Well, greetings out there in YouTube land, and welcome to today's big video featuring the amplifier chassis that is contained in this very nicely packed box. Okay, so without further ado, let's get the box open, get the chassis up on the work stand, and see what we're up against in this challenge. Once again, we have a beautifully packed shipping container here with styrofoam, even a little piece of tape to lift. And look at the packing. We've also got a nice letter here to read, which we'll do in just a moment. So let me set the camera down, get all of this out so that we can inspect it, and then we'll read the letter and see what our job assignment is. Well, I was wrong about it being just the chassis. We got the whole head here. Okay, so I think this is probably a Bassman, but let's get it out of its wrapping so that we can check it out up close. And lo and behold, it is a 1965 blackface Bassman amp. It's in real nice shape. Overall, some damage to the Tolex, but as we will see, this amp has been used for musical performances and all, and you know, while transporting them, they tend to get skinned up a little bit. Okay, so we'll take a closer look at it in just a moment, but for now let's take a look at the letter and see what the owner of this amp is asking us to do. Well, right off the bat he answers a very important question, and he says that authenticity is less important than functionality. As I said, he is a performing musician, so he wants this amp to be very reliable. He purchased it in 1976 for $75. Wow, those were the days, huh? Then it sat unused from 78 up to 2010, where he took it to have it serviced. Okay, they installed a 3-wire grounding cord, removed the death cap, power screen resistors, filter caps, the usual tune-up. Okay, after study and analysis, he thinks it is an AB165, and we can check it out to see if that's true or not. He also says, though, it's been modified to remove some of the unpopular bias and local feedback aspects of the power amp, but it retains the AB165 3-stage preamp. Like I said, we'll check into that. Now here's page 2, and he goes into an analysis. He feels it's a transitional form of the amp between the double A165 and the AB165. It has elements of both circuits. Now that it could well be a transitional model, but also we've seen that sometimes Fender played it a little fast and loose with components so that the really perfect identification of some of these models is made more difficult by the fact that when they left the factory they did not contain the exact component values that the schematic said they did. Okay, here's a list of all his observations regarding the amp. Now we're on page 3, and we're discussing what the problems are with the amp. It says the pilot light appeared to be out. He replaced the pilot light, turned on the amp, and smoke started coming out of it. He unplugged it immediately and looked inside and found that the 6.3 volt center tap to ground for the filaments was burned from the chassis to where it enters the power transformer. Wow, I've been on a hot streak for transformers here lately. Looks like we have a dead short somewhere in the 6.3 volt line that just destroyed the power transformer. Let's hope not. This tells what else he did, and here's what he's asking for. Fix that 6.3 volt center tap circuit, which might involve replacing the power transformer. A little bit of minor hissing. Normally we think of hissing in transistorized circuits, but we'll see. And a few little pops here and there, which can often be from carbon comp resistors warming up. You know that a carbon comp resistor is just a little trail of carbon sealed in like a ceramic sleeve, and if there's little breaks in that trail of carbon, there'll be an arc as the electricity jumps across that gap and can produce the pops and crackles that we hear. Okay, so we'll check into that. Take the AC receptacle out of the circuit. Normally I don't. I can do that if he wants. And then he also wants the ground switch removed from the circuit, and then down here asks that I make a switchable NFB loop, which I've been doing on all of these larger amps. Check for cold solder joints, replace any bad tubes, and he wants a negative feedback loop restored to the amp and made switchable. Now this one's kind of unusual, and I've never done this. Install a middle tone control in the normal channel in place of the AC receptacle that's supposed to be removed from the rear of the chassis. And he goes into some suggestions on how that should be done, as well as a Fender Guru link here. And the Fender Guru, if he says it, I believe it. They're good folks. Okay, so we'll check into that. He wants to know my opinion, and to be honest, it's up to him. If he really thinks that he needs a middle tone control, then by George, we're going to give him one. Okay, so that's a very specific description of what's wrong with the amp and what he wants done with it. I appreciate that. That'll help guide us. So let's go ahead and get started by removing the chassis from the cabinet, and we're going to check for some of these very serious issues that he's already reported. All right, I've removed the back panel and gained access to the inside of the cabinet where all the tubes have been packed separately, as well as the tube shields. Okay, so far so good. Now it's time to remove the 4 chassis retention screws and slide it out of the cabinet. Okay, the chassis has been removed from the cabinet. You see all that RF shielding, which is really just screen door material here, screening stapled up to the top of the cabinet, very typical, with countless staples. We see that we have a AA165 tube chart. We also know that these charts sometimes aren't all that correct in their identification of the chassis. It's just whatever tube chart they had on hand that had the right tubes on it. Okay, so it may or may not be correct. We see that this particular amp was constructed in August of 1965, which coincides with the serial number and our expectations. Okay, so let's take a look at the chassis and circuit. Okay, here's the circuit. We see that the bypass caps were all left in the originals, which probably is not the best idea. If you're going to change out the electrolytic filter caps, you might as well change these out too. They're very important for the tone of the preamp stages. We do see that those blue Mallory caps are present. They're almost always good, and they do contribute to that Fender tone that we expect from amps like this. We see that the original grid blockers were left in place, but that the screen resistors were replaced as we were told in the letter. We also see that the negative DC bias supply cap was replaced. Everything else, all the diodes and the resistor in the bias supply are all original. Now, this was mentioned in the letter, and it's true. Look at this resistor. It comes off here of this particular terminal on the bias pod. It comes over here to the terminal strip, and nothing connects to it. Isn't that strange? And I don't see that anything ever was connected to it. Sort of like the road to nowhere, eh? But over here is the part that causes the pain and the old sphincter, and that is that the center tap for the 6.3 volt circuit is just fried, which may or may not mean that the 6.3 volt winding is fried. Okay, we can hope not. Have to check it and see, but if it is fried, we have 2 ways to go. replace the entire power transformer, or find a place to tack in a 6.3 volt center tapped filament transformer somewhere on this to make up for this particular issue right here. Okay, and the way it happened, I think, remember we were talking about that the indicator bulb was burned out and was changed. It sure looks to me like there is contact between one of the 6.3 volt wires to that bulb and the grounded bracket that holds the bulb. I can test it with a voltmeter, but I'm going to bet you that that's what caused this thing to go up in smoke. Also, let's consider the fact that just after the bulb was changed, this happened. Okay, you know, what are the odds? You got to look at what's led up to an issue. That can help you sometimes. Now, I'm going to warn you about this. There's two like wings out here that protrude from this bulb, and they can rotate like propellers. And both of them have the 6.3 volts applied to them. Really, it's like 3.15 volts to each. But if those little tabs rotate and touch metal, which is very easy for them to do, you too will have a roasted center tap. So be very careful. Anytime you open up your chassis, look in here and make sure that these little wings that the 6.3 volt wires make contact with are not touching metal. I even use super glue to freeze them in a safe position. You might consider doing the same thing. Okay, also that might have been why the bulb didn't work in the first place. Okay, so this is one of those things you just hate to see. Oh man, this wire, well, it's just burnt loose. It's a mess. So anyway, I need some voltmeter, ohmmeter and all to go ahead and test this, but I think for now we see what's wrong with this and what the elephant is in the room, and we just need to figure out the right way to repair it. The only other area that requires some scrutiny here are the electrolytic filter caps that are under that doghouse. And we see that our reservoir caps, instead of being 70 and 70 at 350 or 100 and 100, that's just fine. I do that myself from time to time. So with them in series, it's going to be 50 microfarads at 700 volts. Okay, so that's reservoir caps. Then we have, you can look right here, we have our 20, 20, 20. Okay, there they are in sequence. Then we have this sort of oddball cap out here on the end, and we see that it corresponds to the 8 microfarad at 450 volt electrolytic cap that provides the final filtration for the B plus supply to the plates of the first triode of the 7025 preamp tubes. We see that they, instead of putting in an 8, put in a 22 microfarad cap. We'll have to check into that. It would cause no harm. Remember that this circuit has diode rectification, which is really not that susceptible to damage from a really high inflow when you first turn the amp on because your capacitor values are too high. But this is probably just fine here. I'm sure it's doing a good job. But we need to test these Sprague atoms. Now, God knows they're highly respected. They're probably just fine. We can check, and I'm not really one who loves to replace parts that don't need to be replaced, but we'll check into that when the time comes. So that's our inspection here, our external tour of the amp. Both the rear and front control panels are in great shape, good knobs. Overall, a good amp. And these are the workhorses for all kinds of performing musicians in sort of medium to little upper medium size venues. Okay, so let's get started fixing this up for our customer. I was just checking out the situation here with this terminal of the indicator light bulb. notice that the end of the wire protrudes through and then unfortunately goes down right toward the bracket. Now it's not touching right now, there's a tiny little gap, but watch what happens if this wire moves over. Dead short, a little bit of space. Dead short, a little bit of space. Now, can you imagine you're putting the bulb in out here and you're twisting the bulb to get it in there, the little bayonets to get lined up and all, and you turn it and boom, there's your dead short. Okay, it might have looked okay when the amp chassis was out of the cabinet, but you see that? Now I've never mentioned this before, but it's something that always scares me about these indicator lights on Fender amps. Now the best bet is to clip the wire off the back and then bend this contact away so that even if it rotates, the little stub right here of wire will clear the bracket. And just a tiny little step like that will make all the difference in the world, and you won't end up with that. Okay? So just a word to the wise. Okay, I was poking around a little bit here. Oh my Lord, look at that. With this center tap for the 6.3 volt filament circuit, and wires just started falling out of the burnt insulation. That one just fell out. So there's no doubt this center tap is all burned up, and it would be virtually impossible to try to go in here and remedy that situation. So what I need to do is talk with the owner. You know, I wouldn't even be surprised if his high voltage center tap wouldn't burn up also. See if he wants to replace the entire power transformer, which is probably the best bet, or to try to tack on a, say, 3 amp or higher 6.3 volt filament transformer somewhere on the chassis. Okay, so after I talked with him, I'll let you know what we decided. Recall that 10K resistor to nowhere off of the biasing pot. Well, remember that the owner of this amp thinks it's a transitional circuit, and I'm beginning to agree with him, because we look here at the AA 165 circuit and there's no 10K resistor anywhere. It would be coming right off just to the right side of the potentiometer. But look over here at the AB165, there it is, 10K. Now they ran it over here to a terminal strip, but then they didn't go any further. It's sort of like they were starting to transition to the AB circuit, but really didn't complete the task. Okay, it's sort of left in limbo. Has the resistor that doesn't show up here on this schematic, but that resistor does not go anywhere. Okay, very strange. You know, while we're at it, let's take a look at other differences between the AB165 and the AA165. Here's another one. On the AB, we have 100K, 100K for our plate resistors on the 12AT7 long tail pair phase inverter. Then we come over here to the AA165 schematic, and we see 82K and 100K. Okay, so let's look in at our circuit, and there it is, gray, red, orange, that's 82K. So we have the plate resistors for the AA165 circuit, which again contradicts the presence of this resistor and sort of reinforces the idea that this may be a hybrid circuit. Okay, let's look for another difference. AB165, you got a 0.01 microfarad coupling cap for the second 7025 in the preamp circuit of the bass channel. Let's look over here, and it's, by George, it's 0.047 in that position. Okay, and that's the AA. Looking down here, what do we see? 0.047. So it's a AA coupling cap, okay, not the AB. Well, that's all fine and dandy, you're saying. It should be the same as the AA165 circuit. Well, let's look at some other peculiarities. Look at your coupling caps for the 6L6s on the AA circuit, 0.1, 0.1. Let's look over here, AB165, big difference, 0.022, 0.022. Well, look in here and you see that the coupling caps are the AB165 values. Okay, so completely contradictory to what we would expect in a AA circuit. And then a major difference, the AB165 has a completely different negative feedback circuit compared to the AA. Okay, AA has 820 ohm feedback resistor, and it goes to the cathode of the 12AT7 phase inverter. The AB165 has a 47K NFB resistor with a 0.1 microfarad capacitor and feeds into the grid of the 12AT7. This is the circuit that was in this amplifier, the AB negative feedback circuit. Okay, now the owner of the amp has asked me to change it back to the AA NFB circuit and make it switchable, and I have done that. The way it was done is I substituted an 820 ohm resistor for the 47K. I eliminated the 0.1 microfarad cap, and instead of tying in here to the grid of the 12AT7, I came down here to the cathode. And then I had to add a 100 ohm resistor to ground. And here you see the alteration. There's the 820 ohm negative feedback resistor feeding into the 22K resistor that leads into the cathode, and then the 100K resistor to ground is right here. So I have converted it back to the AA165 negative feedback circuit. Now why, you might ask, and my reasoning is this. Since the negative feedback loop is going to be made switchable, it's my experience that the difference between the NFB on or off is far more noticeable and more useful if it's running through an 820 ohm negative feedback resistor instead of the 47K resistor for the AB circuit. Also, I like the idea of feeding into the cathode rather than feeding in to the grid. So that's why it was done. When we do the audio demonstration, I think you'll see that the difference between NFB on and off is very noticeable, and at medium to low volumes, the NFB switched off is a great asset. And here you can see that the original ground switch has been converted so that now it switches between the 820 ohm negative feedback resistor and the secondary of the output transformer, as seen in the schematic. Here's the secondary of the output transformer through the old ground switch, through the 820 ohm resistor, and into the cathode of the 12AT7. You know, I did some thinking overnight about this problem with the burnt up center tap on the 6.3 volt winding, and it occurred to me, if that burnt center tap did not damage any of the other wires or compromise them or short them, maybe we can get by without the center tap and simply use the 100 ohm resistors from each of the wires to create a virtual center tap, and then use the ends of the winding as is. Okay, and this would save a ton of money and preserve the originality of the amp. Now I have sort of insulated and immobilized all the wires here with some clear silicone, which is set up. That will make sure that nothing bumps into anything else down the road. And now I'm going to install the 100 ohm resistors and replace the old bypass caps, test the non-polar caps, rewire the primary circuit, put in an adjustable or switchable NFB loop, and just the routine overhaul. Then we'll check this. We'll test it, see if everything works, and maybe preserve the originality of the amp as well as save the owner a whole bunch of money. I think it would be a good learning opportunity here to discuss why the loss of the center tap for the 6.3 volt filament circuit is no big deal. Let's look at the purpose that the center tap serves. Once you ground the center tap from that 6.3 volt output, you will be sending out exactly 3.15 volts in each of the two output wires, and they will have opposite polarity. Now that's very important, because when we twist the wires together, the opposing polarity within them will cause the electromagnetic fields that are generated around the AC wires to neutralize each other, which is why these wires are so tightly wound, because the 3.15 volts being carried through each of them is of opposite polarity, and therefore the EM fields will cancel. Now, when you don't have a center tap, no reference to ground, then the output will be 6.3 volts, the same as it is between these two output wires, okay, but it will vary. This one might be 4 volts, this one 2. In other words, any combination that adds up to 6.3 volts is possible from them. Now, when you wind those wires tightly, the varying voltage, even though it's still out of phase, it will not neutralize. If you have 4.3 volts here and 2 volts down here, this one will have a stronger EM field that this one cannot neutralize. So we end up with hum. That's the reason we wind the wires and neutralize the electromagnetic fields. So when you have no ground reference here at the center of the 6.3 volt winding, you can get hum induced in your circuit because of the existence of unbalanced electromagnetic fields in those wires. Now, the common solution to this, when you don't have a center tapped 6.3 volt winding, is to put 100 ohm resistors on each of the lines. Now, remember the strapping resistors that we used across the 70 microfarad reservoir caps? Okay, they were to ensure that the 425 volts is divided evenly between the two capacitors rather than more of it striking one capacitor than the other. Well, it's just the same here. By putting these strapping resistors across these lines, we create like a voltage divider network that ensures that exactly 3.15 volts will pass down each wire, not varying voltage as we saw without the center tap and without the what we call virtual center tap resistors. By doing this, we can get the equal voltage of opposite polarity that when we twist the wires will then neutralize the electromagnetic fields around the wires. So we can eliminate hum even without the center tap. This is what I intend to test here. Since our center tap is gone, then I'm going to use this method with virtual center tap, really strapping or voltage dividing resistors to create balanced output from the winding and therefore eliminate the possibility of AC induced hum. All right, let's review the work that's been done so far. I've replaced the cathode bypass caps with brand new ones that are rated at 50 volts. I've rewired the primary circuit so that the on-off switch is first, then the fuse, and I have completely eliminated the polarity switch from the circuit. I've separated it from the circuit so that I can use it for our negative feedback switching that will make this amp have great tone and bass response even at low volume settings. I have no problems with the electrolytic filter caps that were installed in the doghouse. They are Sprague Adams, which are highly regarded capacitors. Also, here in the negative DC bias supply, things appear to be ship shape, so to speak. So now, let's talk about one other thing here that has been nagging at me, and that is I blamed the burning of the center tap on a short right here on this particular wire and that little wing against the grounded bracket. But there's no burning or discoloration there, and that kind of worries me. It looked like a dead short, but the actual evidence of one is not present. So what I'd like to do is go back and test all of the tubes for shorts in the filament circuit. That's kind of a long shot. Okay, I can't say that I've seen that very often, but you never know. Okay, so let me eliminate internal shorts within the tubes as the possible cause of the immolation of our 6.3 volt center tap. Now, using the trusty Hickok Model 600A tube tester, let's adjust our line voltage, check for shorts, and test the output of the tubes. As you can see, that was a perfectly good tube. Let's repeat that procedure now with the other 5881 and all of the 9-pin preamp and phase inversion tubes. Well, I'm somewhat relieved to say that the two Russian 5881s and the four 12AX7s and 12AT7 all checked out perfectly with no shorts and good emission. And then finally, let's double check to make sure there is no continuity between either of the filament wires and ground. And sure enough, in both cases, there is absolutely no continuity whatsoever. So there's not even a partial short existing right now between the 6.3 volt winding and a ground in the amplifier. And you can see the two virtual center tap resistors to ground coming off of each of the 6.3 volt leads. I didn't have a good matched pair of 100 ohm resistors, so I'm using 150s. The exact resistance is not as important as the fact that they do match pretty well. Some of you may have seen a hum reduction potentiometer in some amp circuits. All that is a virtual center tap. It's just the same as if we ran the 100 ohm resistor to ground here and here, but instead we put a 100 ohm pot between the two outputs, and then to the wiper we'll put another 100 ohm resistor to ground. Okay, then we can dial in by moving one way or the other exactly the right strapping resistance so that we gain a perfect symmetry in our outputs. Okay, the reason for this 100 ohm resistor off of the wiper is, what if you turned it all the way over to here? If you didn't have that resistor, you would have a dead short and you'd end up with an amp behaving just like the one we're working on. So be sure you add a resistor to ground just to protect yourself from going a little too far left or right. Alright, the amp is plugged into the current limiter to protect the circuit in case there's any undiscovered shorts still remaining. I realize when I do the biasing for this rather high wattage output amp, I will have to plug into the wall AC outlet. My probes are connected to the two leads that power the pilot light, so we can see what the voltage is in the filament circuit. Let's go ahead and flip on the power switch. Good news. Remember, the owner was telling us that he couldn't get the pilot light to work. And we look over here and it's 6.63 volts of AC. So it looks like our filament circuit is working just fine. Let's also take a look at our tubes, and we can see, I hope you can see there, it's kind of glary right here, but all of the filaments are lit up. Of course, we'll have to do more testing to be sure that this is a good usable circuit, but for now I think things look really good. Okay, so let's turn it off. And you know, before I shut it down, I went ahead and turned on the high voltage. Tiny little bit of rustling in the background from those carbon comp resistors, but there is no hum whatsoever. So I think this strategy may well work just fine, and for one of the rare instances where you can save like $150 and still have perfectly good performance from your amp. Yay! Since the owner was complaining about some popping and snapping when the amp came off standby, a really good reason for that is these old carbon comp resistors. I think these were probably replacements, but they're just not optimum. I'm using metal oxide resistors instead. I'm going to install them here in the power rail. I bet you these cut way down on the noise. Also, I'm not real thrilled with the way that the electrolytics were installed. I'm going to go back and trim these leads and solder them in where they're nice and angular. There we go with the upgraded connections for the electrolytics, the metal oxide resistors. Naturally, I don't have this particular value handy, so I'll have to go shopping. But for now, that's the way it's going to look under the doghouse. Well, we're out here in the garage, and we see Ollie is happily nestled in her high-rise cat house, all nice and warmly upholstered, with the heater aimed at her, and she's just living the good life now that she's decided to move indoors. Right, Ollie? She's playing hard to get. Here we have Jack happily nestled on the bed in the master bedroom in his towel nest that we make for him to keep him warm and cozy. How are you doing, Jackie? Say hello to the folks out there in YouTube land. He winked at you. Then, of course, we have Casey here nestled, all warm and cozy on the couch in the den, sleeping like the little kitten that she is. Hey, Casey, how you doing? Well, silence means she's doing very well indeed. Good girl. It's hard to believe when you really start analyzing the details in some of these circuits what you can find. Okay, I'm in the process right now of doing the final biasing with the wall AC supply, and I'm hooked onto the plate pins here on the two 6L6 tubes, but I notice a wire that comes out from each plate over here to a terminal strip. This looks pretty darn original to me, and also it's identical to the type of terminal strip that was used down here for the bridge to nowhere. And I'm wondering if this was added in so that they could hook on to do the biasing maybe at the factory. This just doesn't make sense. I can't imagine a tech adding this, and it looks like it's an existing hole and an original style terminal strip. So, you know, I have no idea. This amp really is unusual, and it's like a prototype or something for when they were converting over to the AB format. and they didn't really complete the process. Very strange. An interesting problem has arisen here while I'm doing the biasing. When I turn up the volume on the bass channel, you can hear a little bit of that power sound you get through a speaker, but really not a hum. But listen when I turn up the volume to the normal channel. We not only get a hum, but what sounds like an oscillation in the background. So let's come over here and move some wires around. Well, that's not normal. That one's not so bad. This is bad. Something's wrong. You can hear in the speaker when I'm tapping on the capacitors. We've got an issue here. Let's check what this wire connects to and see if we can't stop this humming and oscillation. Also listen when I turn off the high voltage. Hear that squeal? I think we got an oscillation here. Some sort of a feedback system is going on right here. Okay, so like I said, let's investigate what that wire connects to, what it's leading to. We might have a bad coupling cap to the volume control. Let's look into the circuit and see what we can find. Okay, pin 2, that wire is the one that's connecting the normal input jacks to the grid of the tube. Let's see if the hum is coming from the input jacks themselves. To do that, I'll just disconnect that number 2 wire from pin 2, and then if the tube is creating the sound or something else downstream, then we can focus our efforts there. But if the that oscillation and hum ceases when I disconnect the wire from pin 2, then we know that the problem resides in this area. Okay, I've disconnected that noisy wire from pin 2. I should also say that I've replaced this tube just to make sure the issue wasn't in the tube itself. You know, like a microphonic 12AX7. And it was exactly the same with a good vintage tube. So the issue then, I think, is arising elsewhere than the tube itself. Okay, this way we've isolated the input circuit. Let's turn this on and see if we still have that hum. Okay, I've removed the wire from pin 2 and grounded the grid, because if you don't, it creates all kinds of awful noises. So let's crank up the volume. And we still have the hum. And we're also picking up a local radio station. So it would seem that the issue must reside somewhere between the tube and the volume control. Okay, so let's continue our investigation. Now if you notice, I'm doing this without any kind of fancy equipment. It's just a matter of eliminating variables in a proper sequence. You can do this at home. I'm not even using a volt or ohm meter. Okay, so now the second thing is, what's the connection between this tube and the volume control? Well, it's the plate. Now what if one of these coupling caps, which they're doubling as tone caps, but they're also coupling caps to keep the DC from the plate away from the volume control, what if one of these has failed? Okay, so let's go in and start checking these 3 capacitors. So the coupling tone caps that we're concerned with, 250 picofarads, 0.1 and 0.047. So I've lifted them. Here's the 0.1, we got one end up, 0.047 and the 250 picofarad. Now what we'll see is the DC is coming from the plate of this 12AX7, and they should stop the DC before it can reach our volume control over here. And apparently it's not doing that. Something's not doing it. So let's see if we have any DC leakage on any of these three capacitors. All right, we're turned on here and we're looking at the distal end of the 0.1. And let me remove it. And you see that it doesn't change when I disconnect the probe from the tip of the 0.1. Let's go to the 0.047. There is no difference. Let's go to the little picofarad cap. I'm not seeing any DC leaking through any of these capacitors. Well, you know, one thing I didn't check on is this noisy wire. This, remember when I was just touching it, it was making all sorts of thumping noises in the speaker, so I bypassed it. Okay, now I put in this jumper. Now the jumper is going to act like an antenna for 60 cycle, so we're going to get a 60 cycle hum here, but it's different from the sound we were getting. Let me turn up the volume. Okay, but I'm not hearing the oscillation or any of that. So I'm going to replace that kind of pinkish wire with a shielded cable from pin 2 up here to the volume control and see if we can't cut out whatever the interference is that's given us fits here. Well, I've replaced the wires that go to the grids of the normal 7025, both triodes, to pin 2 and to pin 7. And here you see the shielded cable that I replaced that wire with. Here's the wire here still sticking up in the air. Brought it over here and grounded both of the shielded cables at one end only to a good solid ground. Okay, let's see if that quiets down this normal channel. Okay, we're on, and here goes the volume. Much quieter than it was, but still, let's compare it to the bass channel. Well, still a little bit noisier than that. I'm going to do a little more work here and try to figure that out. Also notice, remember before when I tapped on these wires, there was all kinds of thumping and feedback. Dead quiet. Okay, so I think we've made some great progress. I'd like to try to squeeze just a little more quietness out of this circuit on the normal channel. Well, let's take a look at the biasing results. This is with the current limiter. This is the resistance of the half winding for this tube, half winding for this tube, voltage drop, milliamps of plate current, and the plate voltage, and then when you multiply them together, we see it's 14.94 and 16.73 watts. Fairly low, but when you plug it into the wall and get the full 120 volts AC, look at how the voltage drop increased. The plate current went up, what, about 4 milliamps? And plate voltage went up, what, 15 volts? So now our plate dissipation is 17 watts and 19.4 watts, which averages out to about 18. Notice that these values went up 12%, 13.8%, say an average of around 13% increase when you plug into the wall AC. So on a fairly high power amp like a Bassman, a Twin, Super Reverb, things like that, you need to be plugged into the wall AC outlet when you're doing your biasing. Otherwise you'll end up with false low values. over here, I would have cranked the bias up a bit, but as we see, this is around 18 watts. Now, these are 5881 tubes, which I think are really 6L6GCs, which could have a maximum plate dissipation of 30 watts, 70% would be 21, 60% would be 18. Since they're 5881s, I'm going to go with a 60% value and leave this. This is about an 18 watt average, so I'm going to leave the bias at this setting. Let's take a few moments out from our Bassman repairs and discuss a topic that arose in the last video. Viewers will recall that one of the 6L6s failed in a very dramatic fashion, and in so doing also damaged my Eurotubes bias probes. So I sent them back to the factory, I'm going to say a little over a week ago, and they've just been returned to me. And the total price for the repairs was $0. They installed fresh interfaces for the tube sockets. I guess maybe there was a chance that there was some internal damage to one or both of them. And it turns out that one of the probes that was connected to the tube that burst probably suffered like a flyback voltage from the just instantaneous interruption of the plate current and was damaged internally. They have a flyback voltage protection circuit, but apparently what happened exceeded that, so they completely renovated that probe. The other one was very slightly out of calibration. They recalibrated it back to perfection. So now it's as if I have two brand new Eurotubes probes in very short order. I just got these back today, and I'm going to say that the whole process took maybe 7 or 8 days, and that included shipping, okay, which is incredible. So I'm completely in awe of their fine customer service and very appreciative, and I wanted to relay that to you all who own these probes, that Eurotubes is going to stand behind you through thick and thin, okay? So I'm glad it all came to a very happy resolution. During the preliminary audio testing, the tone and the bass channel was found to be really flat, really not exciting at all, whereas the normal channel sounded fantastic, typical blackface Bassman. So I'm investigating the tone circuit here in the bass channel, and there's a couple things I wanted to show you. Okay, I'm injecting a 90 cycle per second tone into the amp. I'm sure you can hear it. Now, let me crank the bass all the way up and listen to the augmentation, the increase in the bass as I go up. Okay, there was some. You could hear it increase. The bass control does have some effect. But now let me show you something just to show you how inadequate that increase is. Let's go to the normal channel. We'll get the same bass frequency. Now listen to the difference this bass control makes. Wow. So you see, this is the way it should act. This bass control is essentially doing nothing, okay? And that's odd on a bass channel to me, but anyway, we're going to have to investigate that and get this bass control to work as well as this one. Next, I wanted to draw your attention to a little capacitor right here preceding the tone controls in the bass channel. And what it does is it shunts the high frequencies to ground, which would make sense if you're going to use this channel for a bass guitar. But if you're not, like probably 80% of the guitar players, you're maybe wondering why on your bass channel it's so flat and lifeless. It's because of that capacitor. Let me demonstrate for you the profound effect that that little insignificant cap has on the clarity and treble frequencies in your bass channel. I'm injecting a 900 cycle per second tone that you can hear clearly. Now I've removed one end of that cap from the circuit, so right now this is the way your amp will sound without that cap, and this is how it sounds with the cap. As you can see, the presence of that capacitor greatly diminishes the treble clarity of the bass channel, which made sense if you use it with the bass guitar, but if, like most people, use it for regular guitar, then you're going to want to remove that cap. And let me show you where it is so you can do that. Looking in at the left end of the eyelet board, tubes up at the top, you see right here this kind of a reddish colored disc capacitor. I've labeled it 0.01 microfarads. I've lifted one end of it, and that's where you got the strong treble, and when I shorted this to that eyelet right there is where the treble essentially went away. That will really make guitar playing through the bass channel, when that cap's in place, really flat, lifeless, just dead. Okay, no real clarity, no sparkle. So I really think it's important for the really majority of people that use the Fender Bassman amp for guitar use is one of the first steps you might want to take is to remove that capacitor. Now let's address that problem with the bass control having no effect. Let's look at the bass tone control. We see that we have 1, 2, 3 0.1 microfarad caps. Then we look down at the normal tone control, which works a lot better, and we have 1 0.1 microfarad cap and then a 0.05. Okay, so what I advocate is let's remove that 0.1, and I'm going to try several different capacitors in its place, starting with a 0.05, and find a capacitor to replace this 0.1 right here, which is the one I've lifted. It's on the right hand side of those three, and I'm going to find one that does not suppress the bass when it's all the way cranked up to 10. Okay, so, and I'll let you know what I've discovered, and I'll demonstrate it for you. All right, time for the demonstration. Let's crank up our 90 cycle per second tone where we can hear it. This is the original 0.1 microfarad cap in place. Crank it up to 10, almost no improvement, no increase in bass. Now we're going to put in my mystery cap, and let's see if there's a little increase in our bass. Wow, there goes the paint can again. It's easily the equal of the normal channel. Okay, now you've got bass, and then without that removed bypass cap to ground, we've got really nice treble. So now our bass channel is going to be lively, clear, good strong bass, and just have the type of tone we expect from a Bassman amp when we use a regular guitar with it. And the mystery cap, well, I started off with 0.05 and got a little improvement, and I kept going down further and further, and finally at 0.005 I got the same type of bass response at 10 on my bass channel that I got at 10 on my normal channel. So I'm going to install the 0.005 microfarad cap in place of the right hand 0.1 microfarad capacitor that came in the amp. And now I'm going to give you a direct comparison of the bass channel before and after modifications. I have jumpered in the capacitor values that I removed so that right now it's exactly as it was to begin with. Then I will unjumper them and play a few more chords so that you can make a direct comparison. This, the next thing you hear will be the bass channel before. I hope you noticed that that was exactly the same volume, treble, and bass settings. And what a tremendous difference in the before and after. The after was had considerably more volume and treble and bass. And I really think that as the amp came to me, a large percentage of the signal was going to ground. Okay, and now it's not. So I really think there's a tremendous improvement here, and I think now that the bass channel will sound as good, if not better, than the normal channel. Now I'm going to demonstrate the switchable NFB loop. I'm going to play a tune through the amp with the NFB off and on, and I will switch it back and forth so that you can hear the difference. We're just going to use the microphones in the camera for this because I really think that will be adequate for you to hear the significant difference between the two positions of the toggle switch. Well, it's finally time for the audio demonstration of the mighty 1965 Fender Bassman amp. We'll be using our standard 12-inch Jensen speaker cabinet and our SM57 microphone running into a digital recorder. We'll have Ollie and Jack strum a few tunes through the bass channel and then through the normal channel so that you can compare them. Okay, so if you're all comfortably seated, Ollie and Jack are tuned up and ready to go. Well, that's about it for this video extravaganza on the repairs of the 1965 Fender Bassman amp. I really felt like this jewel threw us some serious curveballs and some very unusual issues. And hopefully, through resolving them here in the video, some of you out there will have gained some additional insights and knowledge about how to interpret and repair Fender circuits. If so, then we have achieved our goal. I'd like to take a few moments also to thank our Patreon patrons and PayPal contributors for their generous support of our channel and keeping us on the air for another month. If you would like to join them, I will put links in the video description which will enable you to do so. I also want to thank the gang at Eurotubes for their very prompt attention to the problems that I had from their probes, and it was absolutely no fault of theirs, but they immediately repaired them and returned them to me at no charge. And I'll tell you, that kind of service nowadays is getting to be a rarity, and one that I really appreciate. And finally, a note of profound thanks from all of us here in Rusty's workshop to all of you viewers out there in YouTube land who stick with us month after month, watch our videos, make interesting comments, ask questions, and just all in all, keep us feeling like we're just part of one great big happy family. And that's exactly how I feel right now during this holiday season. So I wanted to wish you all the best and hope that you'll join us in our next video. Thank you so much.